Yes, sir.
Okay. So what I am going to do is discuss two more problems which we have done before in our fluid mechanics class, and then in the second class of today we will start solving some of the problems which require more involvement than what we have covered in fluid mechanics, and move on. So I think some of you would still remember this specific problem where we have a pipe through which a cylinder is falling in a perfectly straight, in a perfectly vertical manner. And the intervening space in between the cylinder and the rod is filled with some liquid. So, of course, this is an idealized situation, as you understand that it's extremely difficult to keep the this solid cylinder straight, and it's going to tilt and hit the side of the cylinder. But if we uh, take it hypothetically that as if it is falling straight, and it's, let's assume that it's also laminar flow, because we understand that if it's not laminar, then there will be additional terms in the Navier-Stokes equation which would account for the transport of momentum due to the formation of eddies and so on. But for the time being, we'll assume that it's perfectly laminar condition and this cylinder is falling. So as the cylinder starts to gain momentum, as it starts to pick up the velocity, downward velocity, then you could see that the distance between the pipe and the cylinder, that's fixed. So with increase in velocity of the cylinder, of course the velocity gradient will keep on increasing. As the velocity gradient increases, there's going to be an increasing shear force which will oppose the motion of the downward falling vertical cylinder. And a point would come where this cylinder will be acted upon by a zero net force, and then it will start moving with a constant velocity. So it is that condition which we are trying to model, trying to see that what would that constant speed be, the vertical speed v of the inner cylinder, as a function obviously of geometric parameters, for example r naught and ri, the operational parameters, which is essentially m, that's the mass per unit length, I think. M is the mass per unit length of the cylinder, and the thermophysical properties of the liquid, which the relevant properties in this case would obviously be the density and the viscosity. So with increasing velocity, the opposing force will also start to increase, ultimately leading to a condition of zero net force acting on this cylinder. So it is that speed, so-called terminal speed, which we are trying to figure out. So as I have mentioned, the condition for constant velocity must be the opposing force is equal and opposite to the downward body force, which in this case is gravity, m being the mass per unit length of the cylinder and L being the length. So that's a straightforward force balance which one can write. And we would like to find out this tau w. And in order to find tau w, one needs to figure out what is going to be the velocity profile in the intervening space between the cylinder and the static tube. So of course the motion is in the downward direction. Let's call that a z component, and it's obviously a cylindrical coordinate system. So what we have is this as the z component of equation of motion, and we need to cancel out the terms which are not going to be relevant in here. So I wouldn't spend too much time on it since you already know about it. This is obviously going to be zero since we are dealing with steady state situation. How about the second term?
It will
Anyone?
be zero.
Which one is zero? Once again, please.
VR dvz by
VR is going to be equal to zero. And in this third term, obviously V theta is going to be zero. And the last term,
the
second,
velocity is not changing in the z direction, so
right. So it's a fully developed condition. So therefore, Vz is non-zero, but del Vz del Z will definitely be zero. And if we so once again we see that the convective uh, contribution to momentum, which is denoted by the three terms on the left hand side, second, third, and fourth, would be 0. It's a steady state situation, so the entire left hand side of the Navier-Stokes equation is going to be equal to 0. Furthermore, if we concentrate on the right hand side, we know that there's no imposed pressure gradient in the present system, so this would be 0. And if we think about the second term, Vz is definitely a function of r. So the downward velocity is a function of the radial position. So this term will remain in here. And Vz, of course, is not a function of theta due to angular symmetry. And as we have mentioned, it's not a function of z. And for Gz, obviously this Gz is to be replaced by the component of gravity which is acting in this. So therefore the Navier-Stokes equation would simply become this. That's the Navier-Stokes equation, reduced form of it, and you can always integrate to find out C1 and C2. And can you quickly tell me what are the boundary conditions for this case?
At r equal to Ra, we'll have Vz is equal to V, and at the outer radius, we'll get Vz is equal to 0.
So you are essentially saying that there's going to be no slip between the liquid and the solid. Wherever the solid is moving, the liquid is going to pick up the velocity of the moving solid that it is in contact with. So at the smaller radius, that means at the cylinder, the velocity is simply going to be equal to the downward falling velocity, constant downward falling velocity, capital V. And at the inner surface of the pipe, the velocity is simply going to be equal to 0. So these two are the boundary conditions, and which would allow you to find out what are C1 and C2. So I will leave that. And therefore one can find out what's the velocity. And if you have the velocity in here, you still have an unknown in this, which is what is going to be so-called terminal velocity of this. Now, in order to obtain the terminal velocity, as we have set up at the very beginning itself, the downward flow, or rather the downward movement of the solid cylinder due to gravity, is going to be counterbalanced by the upward opposing force due to the shear. So I am trying to find out what is the shear, and the shear, assuming that it's a Newtonian fluid, I can write the expression for shear, which obviously contains C1 that we have evaluated in here. And so when we do that, that means tau at the inner cylinder is equal to the mass, the m times g. And once you do that, you get the velocity expression. And of course, here I can find that the velocity is a function of the geometric parameters. It's what kind of material the cylinder is made of, and of course rho and mu. These are going to be relevant in this specific problem. So if there are any questions, this is the time when you can ask me. You can ask me anytime. Is there any question for this specific problem? So this is something which we have solved in our fluid mechanics momentum transfer part, and I'm doing a quick recap of what you have done at the first semester of your second year. Now then, coming to the one of the main themes of working with Navier-Stokes equation for slightly advanced problems, we would like to see that can we make some judgment about the terms which remain after obvious simplification of the Navier-Stokes equation. So what are the relative magnitudes of these terms, and can we then drop some of the terms which would allow us to change a PDE to an ODE maybe, or and then proceed with the solution of this. And herein your understanding will play a crucial role. And one of these problems which we have solved in our fluid mechanics class, again in the coming 15 minutes I'll go through it once again so that you remember. I think many of you will remember this problem, where there are two disks, both are stationary, separated by a certain distance twice b apart, And if you look at z equals minus b and z equals plus b are the locations of the two disks, and there is a hole at the top disks through which the liquid comes in, some fluid comes in, and then once it enters the space in between the two disks, it's going to change its direction and move radially out upon the application of an imposed pressure, where it is defined that the pressure is P1 at the outer periphery of the smaller hole, and it's P2 at over here. This P2 could very well be the atmospheric pressure. So it really does not matter. But the important thing is that the pressure at two locations are known to us. So the problem obviously is more complicated than the way we are going to solve it. First of all, when the liquid comes in between the space, there's going to be a reversal of flow direction, rather a change in flow direction from a vertically downward flow. It's going to become radially outward flow. Now, whenever that happens, there's going to be a region of instability near this hole that we are not taking into account. So multidimensional effects are prevalent in a region close to this entry point, which we are neglecting. When can we neglect that? If the flow rate is not too large, if the velocity is not too large, then we can do that. If it's liquid of high viscosity, then also we wouldn't introduce too much of an error when we assume that, because viscosity is something which brings back order to a system. So high viscous fluid will will create a condition in which all the disturbances die down very quickly, and then it starts to move radially outward. But this is the point where we must appreciate that we have made an approximation in this. So the two radii are provided, R2 and R1, and we need to find out what's the velocity profile in this specific case. So you recall this specific problem? Some of you, any of you? Or okay, let me put it. Okay, is the problem statement clear to all of you? If not, I will explain again, but if you do not say anything, then I'll assume that you have understood the problem, the description of the problem. Is there anything that you want me to repeat? Okay, then we move on to this part of the problem. The first, what I have written is this continuity equation, and in the second, what we have written is, since the principal direction of motion is r, so I have written down the r component of equation of motion in cylindrical coordinates. And we need to proceed with that. So the first one is obvious, that it's a steady state problem. So we do not have any time variation, any transient term in this, and we'll also assume that it's a liquid of constant density. So therefore, all the rows, the densities appearing in these terms can be neglected. That's one part of it. There is no velocity in the theta direction. There's no velocity in the z direction. So the non-vanishing term of the continuity equation would only be this term. So if that's the case, then since 1 by r del r of, or in fact I can write d dr of in fact rho r vr, this become equal to 0. I should have used the normal differentiation signs. There's no reason to write partial differentiation signs. So this would give rise to my VR is something like theta by r. And if you recall your previous classes, you could probably tell me something about theta. Would you be able to tell me what this theta would be? Look at the problem. Think about the functional dependence of VR, and then tell me something about phi, the constant of integration. From the description of the problem, VR is a function of which 1, 2, or 3 directional coordinates, r, theta, and z. This VR is a function of what?
R.
Z.
Okay. Both or any one of them?
Only Z.
Okay.
I mean Z and R. Obviously there was R, so R and Z.
Okay. And why would you say obviously it's going to be a function of R? Can you
Because
expand?
it is VR is equal to phi by R.
No, I can see that, but physically, why would VR be a decreasing function of R?
Because of the continuity equation.
Continuity
So
equation.
the larger R, the area or the circumference increases, so it has to slow down.
Right. So as we move out in the radial direction, the amount of, or rather the extent of area available, which is twice pi r multiplied by twice b. So this r keeps on increasing. So obviously, since the area is more, the mass flow rate is constant, so the velocity has to decrease. So what we have then is VR is a function of r and z. So if you look at this and what we have obtained over here, can you make some statement about phi?
It should be a function of Z.
So phi should be a function of z only. Okay. So the remaining portion of the problem could be to obtain what this phi is going to be. Because if I could find the expression for phi in terms of the parameters that you see in sometimes it's good to start with equation of continuity, which would give you an approximate functional form. I mean, approximate form of the dependence of the velocity on the space coordinates, which in this case are r and z, and we could see that phi is a function of z only. Now, coming back to the r component of the equation of motion, and we wrote the r component of the equation of motion just to make sure to highlight that we have the principal direction of motion, principal direction of movement in the r direction. So that's the component that we have written over here. So the first part obviously would be 0, since we do not have any time dependent situation in this case. How about the second term? Should
It
we?
would stay because it is dependent on R.
So this is going to remain in my equation. And of course, that's not going to be any v theta, no v theta, no vz. So all these terms will disappear. Now, when we come to the right-hand side of this equation, how about del p del r?
It will also stay because there is a gradient, like it is
There
changing R.
is an imposed pressure which is there in the system, and let's consider the third term, del square VR by del theta square. Do we have this term? Should we have this term? Del square VR del theta square, the third term on the right hand side.
No, does not depend on theta.
Okay, so there is an angular symmetry in this, so this is going to be equal to 0. Of course, there's not going to be any v theta in the system. How about the last term on the right hand side? Del square VR by del Z square.
It should be there because VR depends on Z.
VR depends on Z. And if we assume that, so VR obviously is going to be 0 at plus B and at minus B due to no slip condition. And what we have in the orientation of this ensures that I do not have any body force acting on acting in the system. Okay. So what I have then is the what second term on the left hand side, second term on the right hand side, and the last term inside the third bracket for the for this case. So these are going to be the reduced form of the equation of motion. Therefore, if you plug in all these, then your governing equation is going to be the this equation, the del P del R, and this last term which was there in the in the equation. I have what about this term? I know that I have taken this into account first. That's one remaining term, second remaining term, third remaining term. How about this term?
term will be 0 because RVR is only a function of Z. That is 5.
So RVR is a function of only Z. So therefore del del R of a function of Z would also be equal to 0. So that's why I have the governing equation in this form. Now let's see how much you recall from last time. What is before we introduce that? Can you tell me the physical significance of the left hand side and the significance of the right hand side? What is the significant? What kind of a momentum transport are we talking about? Are we expressing by the terms which appear on the left hand side? Convective transport, conductive transport, or something else?
Convective.
And your reason for making that statement?
It's VR, so it's in the direction of R, and then we are seeing that's changing with the direction of R.
Perfect. So whenever the velocity appears independently, or rather I would say velocity appears apart from velocity gradient, most likely it's definitely it's going to be a convective transport. And if you look back at the previous one, this term has come from this, and we know that the left hand side of Navier-Stokes equation is essentially convective momentum. So therefore, this is the first time that we are dealing with a term which is whose nature is convective. So therefore, this is going to appear on this side. This is pressure. This is a flow created due to the pressure gradient, and the obvious appearance of mu ensures that what we are dealing with is a viscous transport term. Now, I would like to solve this, which I cannot do because of I'm dealing with a partial differential equation right over here. And what the I can do is I can put this VR as phi by R and make it simplify it slightly so that this becomes rho phi square by R cube or some form and so on. Any assumption which we can make. If I increase the value of pressure gradient, can I drop any of the terms? If I reduce the value of dPdr, the pressure gradient, can I drop any one of those terms? So think in terms of pressure gradient which you are controlling from outside. You increase the pressure gradient. What about the relevance of the first term and the first term on the left hand side and second term on the right hand side? You reduce the pressure gradient. Again, what are the implications? What's going to be the implication of that on the first term on the left hand side and the second term on the right hand side? All in the value of pressure gradient that you control from outside. If the pressure gradient is more, what happens to the velocity? Increase or decrease?
Increase.
Okay. So if the velocity increases, will convective transport be prominent, or would its importance be reduced?
Prominent.
Prominent. So it's going to be more. So if I think in the opposite direction, if I apply a small pressure gradient, then of course the velocity, the resulting velocity VR is going to be small. And if the velocity is small, then the left hand side of this equation will slowly lose its relevance. the relevance of the first term on the left hand side will become negligible as the velocity is becoming progressively smaller, which will become smaller as you reduce del P del R, the imposed pressure gradient. But in even let's say the pressure gradient is small, applied pressure gradient is small, the left hand side is going to be unimportant. What happens to the second term on the right hand side? Will it still be significant? And if so, for what reason? What would you have to think? Look at the figure and tell me at low values of pressure gradient, the movement of the liquid through the space is small. So therefore, this VR is going to be small and the effect of this convective transport is going to be small. But how about the viscous transport of momentum tau? Will it remain significant? And if so, for what reason? Any thoughts on that? These are some of the considerations which you have to apply for problems of real life problems where you may have to neglect certain things. And this brings us to an interesting variation of the fluid mechanics or the momentum transfer that we are talking about. Anyone having any wild idea? VR is becoming smaller with reduction in del P del R, but the viscous transport is still important. When can that happen? Only that will let me keep this term. VR is small. Any look at the image and tell me when would that be something which we cannot neglect? Apart from the pressure gradient and obviously the choice of the liquid, is there any other geometric condition which you can manipulate?
And 2B is very small.
When 2B is very small. Why would you say that when 2B is very small?
Because that gives it less space to basically spread out, and that del Z value would be small for del V by del Z.
I couldn't hear you very well, but I think I understood what you are trying to say. What I think what you are saying is that the gap between the two whatever disks, if that is small, then even though the velocity is small, the gradient or del Z of del V del Z could still be large. That's a very important observation, which is becoming more and more relevant with the application of fluid mechanics in small scale systems. Now, many of you are aware that the fluid mechanics that we deal with, it has found new usage in situations where the system size is small, where the gap is small, where you are having flow through a microchannel or flow through conduits which are extremely small in size. So the pressure gradient applied could be large in order to initiate flow in such small systems. So therefore the convective part could be neglected since the velocity of the flow is small. But the gap is so small in those microscale systems that the gradient and therefore the viscous transport of momentum will still be substantial. So the pressure drop required to make a liquid flow through a small conduit is going to be phenomenally larger as compared to the pressure gradient necessary to make liquid flow through a macro scale system. So for micro scale applications, which is one of the hallmark of microfluidic applications, the gap being small essentially dictates what kind of pressure gradient you need to apply. So those calculations are those calculations of how would the system size dictate what is going to be the pressure gradient required would be very important for microfluidic applications when you can neglect the convective when you can safely neglect the convective transport of momentum. So what we do then is the major assumption on the nature of the flow. Here we say that there is a negligible convective transport. So convective transport is unimportant, and if the convective transport is unimportant, then this term would be equal to 0. And the name of this assumption, what is the name of this assumption? What kind of a flow is this called? If the convective part is rather small compared to the viscous part, this you forgot, but this is known as creeping flow. So the creeping flow is defined where you do not have any contribution from the convective part of the motion. Now, then my governing equation would simply be equals dp dr equals and you would be able to solve this equation. You would be able to solve this equation with the two boundary conditions. That is, the pressures are the pressure at P equals P naught, at R equals R naught, and P equals P1 at R equals R1. So with these two boundary conditions, you should be able to evaluate what is VR. So assuming a constant pressure difference, I'll leave that for you, is that you would be able to find out the expression for phi, which would simply be equals minus delta P, where delta P is the pressure gradient, imposed pressure gradients P1 minus P2. And as I mentioned, C1 and C2 can be evaluated by the known conditions. So my VR, which I know that it's a function of R and Z, is simply phi divided by R from the equation of continuity, and I can write what is there on the right hand side. And the conditions that the other boundary conditions that you can say is that at Z equals plus B, and at Z equals minus B, the velocity will be 0. That's the no slip condition. So with this no slip condition, now you are in a position to express. I'll leave all these for you to figure out. And this is the final form of the velocity which you have in the small conduit in absence of major convective contribution, convective momentum transport condition to the problem. So this is what the velocity profile would look like, and this is an example of how your analysis of the different terms of Navier-Stokes equation based on their predominance uh, predominance in a specific application situation can be utilized to obtain the velocity profile. And of course, if you have the velocity profile, you could also figure out what is the volumetric flow rate, and therefore the area, it's going to be simply the area which is perpendicular to the direction of flow. So the area that is perpendicular to the direction of flow is simply twice pi r times dz, and we know that rvr is rvr doesn't depend on r. So and the integration is from minus b to plus b. You would get this expression for the total flow rate of the liquid through the space in between two disks when we apply a delta P. This is also another way. This is also the working principle of some of the viscometers, which are used to measure what is the viscosity of a very high viscous fluid, high viscosity fluids, because at high viscosity fluids the momentum transport is principally due to conductive momentum transport, molecular momentum transport, and not convective momentum transport. So here, if you can measure what is Q as a function of delta P, the applied pressure gradient, and making sure that you do not get into a high velocity situation, the unknown here is going to be mu, which can be used for, this expression can be used for measuring the viscosity. Any question to this? Any question that you may have on this? Then I move on to the next problem, which I think I have given this problem as a practice problem to you. I'll quickly discuss this and then have a break. You have an incompressible fluid which is flowing in this configuration. So you have the flow direction, but you have simultaneous injection of the same fluid in a direction perpendicular to the flow. So if this is the x direction in which I have the principal direction, I have some injection in the y direction into the system, and some suction out. The same amount of fluid is being sucked out at the top. So these two are porous plates through which the same liquid is injected and is sucked out, whereas the principal flow moves in the x direction. Okay, so we need to find out the y component of the velocity, and then we also need to find out what is the x component of the velocity. The application to this kind of situations are common in membrane separation processes. In many of the membrane separation processes, when you think about a hollow fiber membrane, in which, let's say, this is a hollow fiber membrane and the solute containing liquid passes through it at high pressure, where the solvent is going to be extracted out of the system. So what you get is a concentrated solution of the solute at the exit. So you start with a dilute solution of the solute present in the system, and then what you get out of it after it passes through the hollow fiber is something which is concentrated in the solute that you would like to retain. There may be number two solutes which are present in the system, and then you choose the membrane in such a way that the molecular weight cutoff is in between the molecular weight of solute 1 and solute 2. So if you have NaCl and a salt of high molecular weight present in the system, and you would like to concentrate that high molecular weight solute, what you need is you are going to probably provide an ultrafiltration membrane or an RO membrane through which the salt can pass, but the larger molecule will not be able to pass. So you can have selective purification of the solute in such a system. So hollow fiber membranes are widely used for desalination, for separation of proteins, for pharmaceutical applications, and so on. This is a slightly modified version of that, in which, apart from the solvent flow out through both the plates, I have a condition in which we have injection and suction at the bottom and at the top plates. When I'm going to teach you boundary layers, you would see that in some cases, in designs of shapes, this kind of suction, this kind of injection at the liquid solid interface, the C and the skin of the outer skin of the shape that is purposefully injected in order to disturb the formation of the boundary layer and to reduce the drag. So this appears to be a theoretical problem, but it has applications in membrane separation or similar such processes, as well as in controlling the drag in a boundary layer in some very special conditions. But anyway, coming back to the problem, what we need to find out is what is the velocity, the x component of the velocity in such a case. Now, I will we can talk about this briefly, and I will leave this to you to solve. The first problem is you can write the continuity equation, which simply says del u del x plus del v del y is equal to 0. And can you suggest something about simplification of this equation? Del u del x plus del v del x. Obviously, the z part is not relevant here since z is too large. So can you say something about the terms of this equation? How about the first term? Will it be relevant? When can I say that del u del x is 0?
Fully developed.
Fully developed flow. So if this is fully developed, this would give rise to this term being equal to 0. So if that's the case, then what I have then is del v del y is 0. So what I have v is simply going to be a constant for all y. Okay. Now, if you look back to this figure, what can you say about Vy in this case? Based on your continuity equation and the notations which are depicted in this figure, what can you say about Vy? We have found out that del v del y is 0. So v is a constant for all y. And if you look at only this figure, what can you say about Vy?
It is equal to capital V.
It is equal to capital V in the entire flow domain. So my V is simply going to be equal to capital V everywhere in the flow field. So next is I can write the x component of the Navier-Stokes equation. So let me quickly write this. And I'm not writing the z part at all. This is the Navier-Stokes equation. Of course, this part is going to be 0 since it's steady state. Second one, second term of the left-hand side.
0.
Since it's a flow, fully developed flow. And the third term.
Not 0.
Because u definitely is a function of y. And therefore, but I can say that instead of v, I can write capital V, the one that I have written over here. And then this part will remain. Obviously, there's a row in front of it. There is definitely some sort of an applied pressure gradient, and that's why the flow is taking place. How about del square u by del y square, del x square? This is going to be, what should it be? This is going to be 0 since u is not a function of x. This will remain and gx is going to be equal to 0. So what I have then over here is mu times d2u by dy square. And let's call it as minus a, where minus a is simply del P del X. That's the constant pressure gradient which is being applied on the system. So this becomes your governing equation, and of course you would be uh, able to integrate this equation and obtain what is going to be u, the x component of equation of motion, and the relevant. Oh, it was there anyway. Anyway, it was already there, so I need not have written the equation over here. So with this becomes your governing equation, and we would assume that there's constant pressure gradient in the x direction, and boundary conditions would obviously be no slip conditions at two different at these 2 points. So at this point there's going to be no slip, and over here there's going to be no slip. I would like to stress upon the point is that even though you do have a velocity, upward velocity, that means Vy is not zero at y equals 0. Vy is not 0 at y equals h, but Vx is 0 everywhere on the plate. That is what the no slip condition is all about. So Vx is 0, but Vy for this specific problem may not be 0. So this is an approximation, this is an assumption where we assume that the flow, upward flow of in the y direction does not affect the no slip condition in the x direction, which is true for most of the applications that we come across. But if it's a case of rapid condensation, rapid evaporation, or very large rate of flow in the y direction, then that Vx may not be equal to 0 at y equals 0 or at y equals h. So even though I am taking Vx to be equal to 0, but we keep in mind that this is an approximation, this is an assumption which would be valid for not a very high rate of evaporation, high rate of conduction, or high cross flow velocity. This velocity is known as cross flow velocity, and the principle of membrane separation, where this kind of cross flow is introduced to disturb the formation of the boundary layer. So this is called the cross flow ultrafiltration or cross flow reverse osmosis, where the purpose of this flow is to disturb the rejected layer of solutes which tend to develop on the surface, thereby clogging the clogging the pores of the porous plate. So the purpose of the flow is to again to disturb the formation of a concentrated layer of solute on the surface. So in absence of a very high cross flow velocity or condensation and evaporation, we could simply use the no slip boundary condition at both x equals both y equals 0 and y equals h. And I will not solve for this since the velocity expression is given to you. You can yourself find out what is the component of velocity. Any questions so far? Okay, if not, then I will take a break, and I'll come back after 5-10 minutes and then continue on some problems which are slightly more involved than what we have been doing so far. Okay, so let's start once again. Can you see the problem statement? One of you, please answer.
Yes.
Okay. All right. Uh, so we'll start this problem, but let me explain it using this specific figure. This is something which is called thrust bearing. So a thrust bearing is where you have a rotating face or a rotating surface, and there is a fixed surface. And in order to reduce the friction in between the rotating one and the stationary one, a lubricant at a very high pressure is made to flow in the small gap in between these two. So the gap here, as you could see, is can see is that is equal to twice h, and you have oil at a high pressure which comes into the space and then start flowing radially outward. The top plate is being rotated. So that's an added complication to this problem, where you could see that here we have a velocity in the r direction as well as a velocity in the theta direction, since the top plate is being rotated. So it's definitely a case of two-dimensional flow, and there would, again as before, there would be some sort of disturbance where the liquid at high pressure is going to come in the plus z direction and then change its direction and move radially outward. Once again, the region very close to this entry point we are not taking into account. We are solving the problem only from that point onwards, where the flow has stabilized. It's being flown, it will flow in the r direction, but at the same time the top plate is being rotated with some velocity, some angular velocity omega. The dimensions are provided, and of course this is open to atmosphere, so you know what is going to be the pressure over here, and the pressure at the entry point can be assumed to be equals P naught. Is the statement of the problem clear to all of you, or is there anything that you would like me to explain once again? So flow between a stationary and a rotating disk. Unlike the previous problem where the two disks were stationary, here one of the disks is being rotated at a high speed, and the practical application of this is in thrust bearing, where obviously you have to choose the lubricant very carefully such that it can sustain its purpose. That is, there's not going to be any viscous breakdown of the liquid. We're not solving that part of the problem right away, but I could tell you some complexities of something that we need to keep in mind while working or while choosing the lubricant for such a system is that the gap here is very small. And as the gap here is very small, the liquid layers are going to move past one another with a very high speed. That means the relative velocity or the velocity gradient in this case is going to be significant, tremendous. So once that happens, something similar to solid friction, what you get when a solid block is being pulled at a high speed over another solid block, what happens is that there's going to be some sort of a dissipation of energy. And that dissipation will manifest itself by an increase in temperature in between the two solid surfaces. Something similar to that also happens for the case of liquids, where this kind of dissipative energy which is lost due to viscosity of the liquid and due to the large velocity gradients which is apparent in small size systems, some amount of heat is going to be generated for such cases. Now, once the heat is generated, the temperature will definitely rise of the oil, and a point may come where the operating temperature of the lubricant will be exceeded. And if that happens, then the lubricant will lose its property, and therefore the two surfaces cannot be kept separated with a reasonable separation. And this kind of viscous dissipation, viscous breakdown is to be calculated before you choose a specific lubricant. So how do you calculate the temperature field in such a situation is also important from a transport phenomena point of view. But we are not solving that problem right now. We will take up this problem when we discuss about heat transfer. Here what we are doing is essentially a problem of momentum transfer where we would like to see what is the velocity profile in such a case, but more importantly from an application point of view, what kind of a load this top moving plate can can take on. So if you press this liquid by placing a weight, then of course how much of weight you can place on the top plate is going to depend on the flow of the oil at high pressure in between the two surfaces. So the weight it can support is indirectly related to the flow. So it's the interconnection between the weight and the flow is the objective of the present problem. Now to do that, this problem has to be broken down into several small segments, and it will have to be answered part by part. So that's what we are going to do. So our aim is to obtain what is the weight that the top plate can support due to its rotation and due to the flow of a lubricant at high pressure gradient condition through this. But at the same time, one has to keep in mind is that the leakage rate of the oil cannot be too large. If the leakage rate is going to be too large, then you need to replenish this oil at regular intervals, which is kind of inconvenient. So we also have to keep the flow rate small. So therefore, I have explained this problem. The outside pressure is P atmosphere, whereas the pressure from R equals 0 to R equals R0, that means the smaller hole through which the liquid comes in, is equal to P naught. Okay. Under laminar flow conditions, we're going to assume that both VR, the radial velocity, and V theta will be non-zero, and P can be assumed to be a function of R only. As the Z, the gap between the two disks are going to be small, so therefore P is there is not going to be any variation, any tangible variation of P with Z. It's a function of R only. This statement is important. Neglect convective and body force terms in equations of motion. This is important but defensible because we know that the velocity, as I have mentioned before, is small. So it's the convective part can simply be neglected, and in small systems you would I would discuss it even further later on and in some other course, that the body force becomes unimportant as the system size is reduced. As the system size is reduced, the surface forces become important. Okay? Whereas the body forces will become rather small, because if you think about the surface force part, let's talk about surface tension. And if you think about the body force, one is proportional to L square, the other is proportional to L cube. So as L is progressively reduced, the body force will fall faster, will reduce faster as compared to the surface force. So when the system size becomes very small, of the order of hundreds of microns only, then the body force has no role to play, whereas surface forces will predominate. Okay, so that's why I could safely keep the body force terms out of the equations of motion, as the gap between the two disks are quite small. And for slow flow, I can always drop the convective term. So the first part is the first part of the problem is that start with the equation of continuity to obtain the functional form of VR. So this is your equation of continuity in cylindrical coordinate systems. So if it's the cylindrical coordinate system continuity equation, so this is going to be 0, since we we do not have any transient. The v theta. What about this third term, del theta of rho v theta? First of all, do we have v theta?
Yes.
And how about del theta of rho v theta?
Probably 0.
Why probably? Why not definitely?
It's symmetrical, so I think it should be 0.
Yes, its angular symmetry is there in this. So therefore, even though v theta is not 0, del theta of v theta is going to be equal to 0. How about del z of rho v z?
There is no
0.
Someone said zeros. Did someone say at the beginning something else, which I didn't catch? The first student.
Vz is 0.
Vz is 0. So even though we understand that there is a Vz, that there exists a Vz right over here, but as I said, my region of analysis does not include this portion. So everywhere else, my Vz is simply going to be equal to Vz is simply going to be equal to 0. So from here, what I can write as before is that my Vr is simply going to be some constant which we understand is a function of z only as before, divided by r. So that's the first part of the problem. So therefore equation of continuity gives me a functional form of Vr. The second part says that show that v theta equals this form has been provided. Okay, this has been provided. We need to show that this satisfies the theta component of Navier-Stokes equation. Okay, so here we have the theta component of the Navier-Stokes equation, and from the statement of the problem, can we make some simplification? Is there any simplification that can be made from? I'll go back to the statement of the problem once again. Look at this statement and tell me if you can see something which could be of use in that part.
Convective and body forces will be negligible.
Convective and body force terms in equation of motion can be neglected. So if you look at the fourth line, it gives us some condition, and therefore which is going to be 0 if the convective part can be neglected?
Left hand side.
The entire left hand side can be made equal to 0 because that refers to the convective part. And of course, this body force term will also be can also be neglected. How about the first term on the right hand side? First
There
term,
is no pressure gradient along theta. It's just along r.
right? It's only along r, not along theta. So this part would be equal to 0. Any other term which you think you can neglect?
D square v theta by d theta square.
The second term inside the third bracket, and the reason this one you are talking about, right? Del square v theta by del theta square, this term. So v
Yes.
theta, even though it is present, its angular is symmetric in an angular way. Its angular symmetry is there, so this would be 0. How about the next term, del square v theta by del z square?
This will not be 0. I guess.
Because it's going to have a finite non-zero value at the top plate, and it is going to be 0 at the bottom plate due to no slip condition. If anyone is having any question, please let me know, and I will explain it once again if necessary. So v theta being non-zero due to no slip condition at the top plate, it has some value, omega times or whatever, twice pi r omega r or whatever. Whereas at the bottom it's going to be equal to 0. So this will remain in the equation. And of course, as before, due to angular symmetry, this part will not be will be 0. And however, this is however this is going to remain in the expression. So what I have then is del square v theta by del z square should be equal to minus or plus, minus, doesn't matter, mu del r 1 by r. This is only these are the two terms which are only going to remain. Now if you
Sir, mu will be not there,
yes,
I think.
mu right, mu will cancel from both sides, so mu will not be there. Okay, so now if you plug in the supplied form of v theta, you would see that the left hand side is simply going to be 0 and the right hand side will also be equal to 0. Okay, so therefore this would be equal to 0 and this would be equal to 0, such that it satisfies so the form that is provided satisfies the theta component of the Navier-Stokes equation. Any question? Okay, then I am moving on to the third part of the problem. The reason these different parts are provided is to give you an idea. Ultimately, our aim is to find out what is the load that the top plate can sustain. The third part says, write the r component of the Navier-Stokes equation. We are dealing with r and theta both in this case, because if you recall that the principal directions of motion are no longer only r, there is motion in the theta direction as well. So we need to write both the Navier-Stokes equation, both components of the Navier-Stokes equation, and try to see if we can make some sort of a simplification in this case. As before, as has been mentioned, that the convective part can be neglected, so the entire left hand side of this is going to be 0, and the body force term will be 0 as well. How about the first term on the right hand side? Can I set it to 0? Del P del R. I'll go back to the figure once again. Del P del R, can that be equal to 0?
No.
No, sir.
So there is definitely a very large pressure gradient which is present that forces the liquid to move in the small space, small gap in between the two surfaces. So del P del R will obviously be present in this specific case. How about the first term inside the third bracket? Will it be 0 or will it be non-zero?
Non-zero.
Non-zero. Okay. Any other opinion on this?
RVR is a function of Z, so maybe it should be 0.
RVR, as you could see over here, is a function of Z only. So that's why the first part comes that the equation of continuity provides you with a specific functional form of VR, at least in terms of R. So RVR is not a function of R, RVR is a function of Z only. So if RVR is a function of Z only, then this part will be equal to 0. How about the second term, del square VR del theta square?
0 due to symmetry.
0 due to symmetry. Del square VR del Z square?
Non-zero.
Non-zero because VR is a very strong function of Z. It's 0 at some point, some velocity at a location not far from the original location. So the gap is small, so there is definitely a large velocity gradient present in the system. And if there is a large velocity gradient present in the system, then the viscous transport of momentum in that direction at least would be substantial and cannot therefore be neglected. So what I have then over here is the entire governing equation is simply going to be del P del R plus mu del square VR by del Z square. So this is going to be the equation that we need to calculate. Okay. So one I can also multiply both sides by R and make it R del P del R is equal to mu times del square R VR by del Z square. Okay. Um, from the Z component of equation of motion, so we know that del P by del Z would be equal to 0. As I mentioned, since the gap is too small, the pressure doesn't vary at all in the Z direction. So therefore P is a function of R only. So I can write P as P of R, and therefore R del P del R is equal to mu times del square R V R by del Z square. So the last one which I have written, R del P del R and mu R square mu del square R V R by del Z square. Can I say that RP, because I have to show that R del P del R is a constant. Looking at this, can you say that it's a constant? Can I say that mathematically? I'll go back once again for you to figure out. Look at this. RVR is FZ. Now you tell me.
Not necessarily.
Can you be a bit louder, please?
Not necessarily, because f of z needs to be a quadratic function for that to happen in z.
Okay. Can I say something about what is the if I look at the right hand side, is it a function of r? Is it a function of z? Or it could also be a constant. Doesn't matter. But can I say something about the right hand side?
It's a function of z.
It is a function of z. If I look at the left hand side, is it a function of z or is it a function of r? Or a function of both?
Function of R.
Pardon me? My question is the left hand side r del p del r, is it a function of z, a function of r?
R.
It's a function of r. So what I have is my left hand side is a function of r and my right hand side is a function of z. If these two are equal, what does it mean?
They are constants.
R del p del r has to be a constant. Okay, so understanding the functional dependence, let's call it as K, understanding the functional dependence of the terms of equation of motion, I mean Navier-Stokes equation, would give me important information on the functional dependence of the term. So my continuity equation tells me that RVR is a function of Z. So at the most, the right hand side of the equation, reduced equation, which we have obtained from Navier-Stokes equation, could be a function of Z, whereas the left hand side is definitely a function of R. So what I would get is R del P del R is a constant. This gives me another interesting result is now I am in a position to evaluate the pressure distribution using the appropriate boundary conditions. How do I do that? I know that my R del P del R is a constant. So I start with I start with that as R, in fact dp dr, it's a function only of R, is some constant k. And we also know the boundary conditions are at R equals R naught. My pressure is equal to P naught, that is the inlet pressure. And at R equals capital R, at the outer edge of the two disks, my pressure is equal to atmospheric pressure. So with this, I can calculate what is the expression for K, the constant over here. It's P0 minus P atmosphere ln R0 by R. So that is the constant, and therefore I can calculate, I can find out from here that P is equal to K ln R plus C1, and you can do the rest. I'll leave that for you. Do you know why these red lines suddenly appear? What am I doing wrong? Let me just.
So maybe your desk is touching the scribbling pad.
Could be. Anyway, you because I cannot delete this thing right now. The entire thing will be deleted. So you remember that this is something which I did not intend to do. Probably it's my destiny. Absolutely, you're correct. Anyway, so I'll write it once again. And C1 can be calculated. So K can be calculated, and the expression for pressure would also be known to us. So what I have then is the pressure distribution is known to me. After this exercise, my pressure distribution is known to me. So I'm slowly moving towards finding out the load that it can support. The vertical load the bearing can support in this case. So to do that, I'll go back to my previous governing equation, which is R del P del R, which is this. that R del P del R is this. So since del P del R functional form is known to me, I should be able to find out what is VR. And it would be apparent to you why this VR is important. So K, the constant which I have evaluated over here as mu, and then I would be able to integrate it twice to obtain what is VR. And can you tell me what are the boundary conditions on VR that you could suggest? It's with relation to Z.
Zero at the two plates.
Zero at no, not zero at the two plates. I'm sorry, zero at the
Zero at the bottom plate and the velocity of the moving plate at the top plate.
okay. I'll come back to this. What are the conditions? You tell me. Let's call it
So
as
it
plus
used to be
H and
zero
minus
for
H.
both plates because
It's
for the top plate V theta is equal to V theta is non-zero but VR is zero.
so that is another mm, another characteristic of no slip condition which I wanted to uh, clarify over here. At the top plate, as you have correctly pointed out, my V theta is not zero because V theta is simply going to be equal to omega r or twice pi r omega r, whatever it is. But at that point, VR would still be equal to zero because there is no motion of the liquid in the R direction at the top or at the bottom plate. So therefore, the relevant boundary condition for both cases would simply be at Z equals H with VR would be equal to zero, and at Z equals minus H, VR would be equal to zero. So I should be able to evaluate, which you can do. I will not do all the steps over here. So VR would simply be equal to K, the value of which I have already derived. This is what the velocity distribution would look like. And once I have the velocity, then I should be able to find out what is the flow rate, which is obviously from minus h to plus h. That's the flow domain. And it would be VR the same way we have done before, twice pi r dz. So twice pi r dz. So with this, by plugging in, integrating and plugging in the numbers, I'm going to get this as P minus P atmosphere. That's the applied pressure gradient. Ln R by R0, the geometric part of it. 4/3 pi h cube by 3 mu again. So the pressure difference is simply going to be, the flow rate is simply going to depend on the applied pressure. It's going to depend on the geometry. It's going to depend on mu, the viscosity of the liquid in here. Why don't I have rho in this expression?
Volume flow rate.
Okay, it's volume flow rate. But if I think in a different way, see, the effect of rho is more or less unimportant in the development of the equation because the convective part of the momentum transport is completely neglected as per the statement of the problem. So that is something which we can keep in mind. But axial load, that is what we have to find out. Um, I'll go back to the figure once again. We have everything that is required for our calculation. But what would be the expression for axial load? think in terms of high school physics. What is the axial load?
Pressure into area.
Pressure into area. Is it pressure or pressure difference? I mean, the atmosphere, is it pressure or gauge pressure? Is it P or P minus P atmosphere? In order to calculate that, let's think of a strip over here. The pressure in here is P. Now you tell me this what would be the expression for load? If you recall, the force in this case is always expressed, if you think about Bernoulli's equation, which you have done in your fluid mechanics, it's always the gauge pressure that is used. So the effective pressure in that slice that I have drawn is going to be P minus P atmosphere. But what is the expression for the axial load? Is it P minus P atmosphere? That's essentially force per unit area. So what I should multiply this with?
Area of that strip.
Area of that strip. And what is the area of that strip?
2 pi r dr.
2 pi r dr. So that's the force supported by this small portion dr. So what is going to be the complete expression for axial load?
Integral of that throughout all r.
Throughout all r or some other r? I mean, what are the limits on that integration?
R naught and capital R.
R naught and capital R. Fine. So what I have then is the axial load, as you have correctly identified, is going to be P minus P atmosphere, which is the effective pressure multiplied by the area of this strip. And this is to be integrated from R naught, the inner one, to capital R. That is going to be the axial load. Any question? And we have already seen what this P minus P atmosphere, P minus P atmosphere is simply going to be K times ln R0 by ln R0 by R. Okay, so that's what this is all about. But is there something else that I'm missing here? I understand that this is the actual load, but am I under-predicting or over-predicting the value of the actual load? I'll go back to the figure once again. Is there something that I need to?
Sir, weight of the fluid?
Weight of the fluid, no, that doesn't matter. But did you identify all the forces? I mean, all the pressure related forces in this? Did you not? Yes, please go ahead.
Sir, I was thinking that maybe because the top plate is moving, so there will also be a force because of this rotation.
But the rotation is in a direction which is perpendicular to the z direction. So its rotation would not impart directly any change in the pressure that is on the system, that is there in the system. But yes,
We did not account for the load from 0 to R naught.
0 to R naught. So what would that expression be? That so-called contribution from that area would be
P naught pi R naught square.
okay. P naught minus P atmosphere, because we
P naught
always
atmosphere, yes.
express in terms of So this would be the total expression for the axial load. And we assume that the pressure is uniform from 0 to R naught, which is P naught. And we know from here that P minus P atmosphere is simply K times ln R by R, which we have seen from our analysis of the pressure. So therefore, I'll leave that to you, that the final load is simply going to be P pi times the effective pressure at the two ends so this would be the total load that the bearing can support. Okay, any question? So what I tried to explain through the use of this this one is that sometimes a complex problem can be divided into several parts. For example, the way what we see in here is many times equation of continuity plays a very important role, at least to give a functional idea of the functional form of one of the velocity components. This is something which has been provided. Okay, so this is many times you wouldn't be able to solve for this velocity profile completely, but your experience tells you that it could be of some form. Okay, but even if it's of, even if you propose some form for the unknown velocity profile, you still have to show that it satisfies the Navier-Stokes equation. So a proposed form of V theta will have to be verified at least that whether or not it satisfies the Navier-Stokes equation. Whether this is the correct form, final correct form, that's open to question, but at least it meets the necessary condition that it has to satisfy the Navier-Stokes equation. Then you deal with the other non-zero, other important velocity direction, which is important. For example, the R component in here, and there you could see that you are slowly getting towards a pressure distribution, because the moment you have to find out the, you are asked to find out the what is the load that the bearing can support. You know that the bearing can support a load which will definitely be related to whatever be the pressure variation inside the small gap in the R direction, and that in order to do that, so P variation of P with R is something that is important, and that you can only evaluate if you solve the R component of the Navier-Stokes equation. So you solve the R component of the Navier-Stokes equation, taking into account that the convective and body force terms are to be neglected, which is definitely something that is justifiable. So the use of the R component of Navier-Stokes equation gives rise to R del P del R is a constant. If R del P del R is a constant, and you could see from the form of the equation that R del P del R is a function of R only, whereas the right hand side is a function of Z only. So together they must be equal to a constant which we denoted as K, and then this could be integrated with the two known boundary conditions of pressure at P naught and P atmosphere at two different values of R naught. So you get the pressure variation, the pressure distribution with the appropriate boundary conditions. Once the pressure distribution is known, then the vertical load is simply pressure difference, that means the gauge pressure multiplied by the strip of the area on which it is working, integrated from the two known values of R and R naught, plus the pressure, plus the load which is due to the small gap, small area over here. So this is a very solid example of the use of Navier-Stokes equation. Any question to up to this? Okay. I have two more problems which I think are going to be very important, and it would give us some idea. Let me see what I have. Which problem I can, no. Both the problems are important, Both the problems are a variation of the problem that we have handled just now. I do not have time to go through the solution, but I can only introduce the problem to you such that from next class I can simply start with the solution itself. Many of you are aware of any problem of transport phenomena. I will always try to clarify whether there is a practical application to this process. So the process that we are dealing with in case is known as the application of a photoresist on a silicon wafer. Now, those of you who have some idea about how a circuit that you develop in AutoCAD is to be transferred onto the surface of a silicon wafer for subsequent processing, you know that there is a chemical called photoresist, and the photoresist is initially coated on the surface of the silicon wafer by a process known as spin coating. So what is a spin coating? The wafer is kept stuck to a chuck, and the chuck rotates at a very high speed. So when it is rotating at 4,000 or 5,000 RPM, there are recipes which will tell you whether you have to ramp it up to a high speed and how long it will be rotated so that you get a fixed thickness of the photoresist liquid on the silicon wafer. That's a separate story. But you put a drop of the photoresist on the rotating silicon wafer, and since it's rotating due to centrifugal force, the liquid is going to wet the silicon wafer and will move out towards the periphery, resulting in an uniform thickness that will decrease with time. The thickness will decrease with time because of the rotation. Ultimately, it come to more or less a constant thickness. You stop the chuck at that point, you bake the silicon wafer with the photoresist on it. So once it's baked and solidified due to cross-linking of the polymers which are present in the photoresist, then you expose it using UV light through the mask which you have prepared using some design tool like AutoCAD on a chrome plated glass. So the glass with the image of this circuit is brought very close to the silicon wafer with photoresist on it and exposed with UV light. The UV light plays an important role in these photoresist. Photoresists are of two types. One is negative photoresist and the other is positive photoresist. When it is exposed to light, the exposed regions either gets solidified, either get strong, or they will remain soft, and the other portion is going to be strong. So when you expose it, the image essentially gets transferred on the photoresist coated silicon wafer, and then when you develop the photoresist, the image remains on the photoresist, the rest will go away. And then you do several other processing steps by which you etch the silicon wafer, you etch the photoresist, and the circuit gets transported on the silicon wafer. So the entire process is very sensitive. It depends on several process conditions, mostly what is going to be the rotational speed of the photoresist coated silicon wafer such that you get a known finite thickness of the photoresist on the silicon wafer, and then subsequent steps so as to get the circuit on the wafer. That's a very, very important step, very interesting. Chemical engineers play a major role in finding out the entire process. So we have a lot of possibility for application of chemical engineering in this. Apart from the chemical vapor deposition or other techniques where also chemical engineers play a very important role. So the problem that we are going to solve next is that you have a wafer and a coating which is made of photoresist, and then it is being rotated at a high speed. Now, if most of the cases the coatings are of the generally of thickness several maximum maybe 100 microns, not more than that. So you start with 100 micron, but as it is being rotated very at a very rapid rate, the thickness starts to decrease. And then it more or less reaches a constant thickness of coating. This H becomes a constant after some time. Okay, so it's a viscous Newtonian liquid which is being applied on a rotating wafer, and the process has angular symmetry. The rotation rate is constant, and this part I have underlined. The film is thin, it's very thin, so there cannot be any real pressure gradient because the top is open to atmosphere, and the accelerations and body forces are unimportant for this case. And the thin film moves with the substrate as if it's a rigid body. So V theta is not a function of Z. So if you compare with think about the previous problem which we have done, where there is a solid plate which is being rotated, here this is open to atmosphere. The liquid is in contact with the atmosphere, it's being rotated. The thickness is so small that the body force, pressure gradient, all these can be neglected. Ultimate aim is to obtain the variation of the thickness of this film, which is denoted by H in the final expression. H naught is what you have at the beginning. Omega is the rotational speed. Rho and mu are thermophysical properties. So this kind of a relation, this is not a correct relation. I mean, this relation is you would like to know, such that as a practicing engineer you can tell that in order to obtain a constant some desired thickness of the photoresist, you need to rotate it at this velocity, angular velocity, for this much amount of time. So this type of design equation is going to be extremely useful to the practicing engineer, and your job from transport phenomena point of view is to come to an expression like this. So there are 4 steps to this problem, which I will discuss with you at the next class, but the importance and significance of the problem I try to establish through the discussion now. Do you have any question? Okay, if there are no questions, then we will take up this problem as the first one in the next class, and one more problem after that before I move on to boundary layers. So you could see that some of the problems which you are discussing in today's class are different from what you have done in fluid mechanics, and I mean not different in the sense that they're more involved than what you have in fluid mechanics. So that's all for today's class. Unless you have a specific question or any questions, I will end the class now. Is there any question? Is there any question from any one of you? Okay, in that case, thank you very much. We'll meet again on Wednesday.
Thank you, sir.